Something unusual happened in January 2026, almost no one noticed. A powerful solar storm pushed the northern lights as far south as Texas. 4 days later, a historic blizzard collapsed power grids, supply chains, and entire cities across the United States. Officially, these events are considered unrelated. But in the narrow window between them, the polar vortex destabilized and broke apart. Do you think it's just coincidence that a solar storm, a polar vortex collapse, and a historic blizzard all happened within days of each other? If you're curious where this leads, subscribe and stay with me. Let's start with what we know for certain. 3 days before any of this started, on January 15th, a sunspot the size of Jupiter rotated into view facing Earth. Sunspots aren't just dark patches. They're regions where the sun's magnetic field has become so twisted and concentrated that it suppresses the normal convection, bringing heat to the surface. The darkness is relative coolness, only about 6,000 degrees instead of the usual 10,000. But that twisted magnetic field has enormous energy stored in it. Like a rubber band wound too tight, eventually something has to give. At 9:30 in the morning, universal time it gave, the magnetic field line snapped. An X-class solar flare, the most powerful category we measure, erupted from the sunspot. For about 20 minutes, the sun's X-ray output in that region increased by a factor of 10,000, but the flare was just the trigger. What it unleashed beneath it was far more dangerous. 1 billion tons of plasma superheated gas so hot that electrons have been stripped from atoms, tore away from the sun, and began racing toward Earth at 2 million miles per hour. This is a coronal mass ejection, the sun literally throwing a piece of itself at us. It carried its own magnetic field, compressed and twisted by the violence of the eruption. And here's what matters. When this magnetic cloud reaches Earth, if its field is pointing in the opposite direction from our planet's field, they can connect. Energy can flow from the solar storm directly into our magnetosphere with devastating efficiency. The plasma took 3 days to cross 93 million miles. Early morning on January 18th, it arrived. The collision happened at 4 in the morning UTC. Satellites monitoring the solar wind a million miles upstream detected it first. Wind speed jumped from 400 to 900 kilometers per second in minutes. The magnetic field strength spiked to 8 times normal levels, and critically, the field was pointing south directly opposite to Earth's northward field on the day side. Perfect conditions for magnetic reconnection. Earth's magnetosphere, that invisible bubble of magnetic field protecting us from space radiation, compressed like a balloon being squeezed. The boundary that normally sits 40,000 miles from Earth got pushed back to 25,000. Magnetic field lines stretched, twisted, and began snapping and reconnecting in a process that transfers enormous amounts of energy. The ionosphere, that layer of thin air 60 to 300 miles up where atoms are ionized by solar radiation, suddenly found itself absorbing gigawatts of power. Not theoretical gigawatts, measured gigawatts. Instruments on the ground and in space recorded it happening in real time. The thin air up there heated by hundreds of degrees. Electric currents began flowing horizontally across the polar regions, driven by the energy pouring in from the magnetosphere. These currents were so strong, they created their own magnetic fields, which ground stations detected as massive disturbances 10 times larger than normal daily variations. And then the sky started glowing. Auroras happen when charged particles from the sun, funneled by Earth's magnetic field toward the poles, crash into atmospheric gases and make them glow. Oxygen gives you green and red. Nitrogen gives you blue and purple. It's essentially a natural neon sign 60 miles up. The reason you normally only see auroras near the Arctic and Antarctic is simple physics. Earth's magnetic field lines converge at the poles. The particles follow those field lines. The auroras appear where the field lines intersect the atmosphere, which creates a ring around each pole, called the auroral oval. For auroras to appear in Texas, that oval has to expand 1,500 miles south of its normal position. This requires the magnetosphere to be compressed so severely that field lines connecting to much lower latitudes get pulled into the interaction. On the night of January 18th, people in Houston looked up and saw green light rippling across their northern horizon. Verified photographs came in from Birmingham, from Memphis, from Oklahoma City. Some reports even came from northern Mexico, though those are harder to confirm. Scientists who study auroras calculated that the energy being deposited into the polar atmosphere during this storm exceeded 500 gigawatts at its peak. For comparison, the entire United States power grid operates at around 450 gigawatts. The storm was dumping more energy into the upper atmosphere than every power plant in America generates. Where does that energy go? Some of it creates the pretty lights. Some heats the air, some drives electric currents, but energy is conserved. It doesn't vanish. It has to cascade through the system, transforming from one form to another, moving from one atmospheric layer to the next. That's physics. That's not debatable. What's debatable is how far down through the atmosphere those effects can reach, and whether they're strong enough to matter for weather. 2 days after the solar storm peaked, meteorologists monitoring the stratosphere noticed something odd developing. The stratosphere is the layer between 10 and 30 miles up above where weather happens, but well below the ionosphere. It's stable, predictable, and home to one of the most important atmospheric features for winter weather: the polar vortex. This isn't the vague polar vortex that weather reporters blame for every cold snap. The actual polar vortex is a specific phenomenon. It's a band of strong westerly winds moving at over 100 miles per hour circling the Arctic in the stratosphere. It forms every winter when the pole goes dark and temperatures plummet, creating a massive temperature difference between the Arctic and lower latitudes. That temperature gradient drives the winds. When the vortex is strong and circular, it acts like a containment system. The coldest air stays locked over the pole. The jet stream in the troposphere below flows smoothly. Weather in the mid-latitudes remains relatively mild for winter, but the vortex can break. Sometimes waves of energy propagating up from the troposphere disrupt it. Sometimes complex atmospheric dynamics cause it to suddenly warm and weaken. When this happens, the containment fails. Arctic air spills south. The jet stream becomes contorted. Severe cold snaps follow, usually 1 to 2 weeks later. On January 20th, stratospheric analysis showed the vortex was distorting. Temperature measurements indicated warming developing over one sector. The circular wind pattern was elongating, weakening on its western edge. By the 21st, it was clear the vortex was in the early stages of disruption. This matters because polar vortex disruptions don't happen randomly. They're triggered by specific atmospheric conditions. Sometimes it's a buildup of planetary waves from the troposphere. Sometimes it's sudden injection of heat or momentum into the stratosphere. And sometimes, according to a handful of research papers that most meteorologists ignore, it's preceded by strong geomagnetic activity. A low-pressure system that had been developing over Oklahoma on January 22nd suddenly found itself with access to an enormous mass of Arctic air that had escaped from the broken vortex. The temperature gradient was extreme. Warm, moist air from the Gulf of Mexico colliding with air that had been sitting over the North Pole days earlier. The storm explosively deepened. Its central pressure dropped 28 millibars in 18 hours, well past the threshold meteorologists call bombogenesis. Winter Storm Fern went from a modest weather system to a historic blizzard in less than a day. Dallas recorded 8 degrees Fahrenheit. Birmingham got 12 inches of snow. Kansas City saw wind chills of -45. The snow fell so fast, 3 inches per hour, in some places that highway crews couldn't keep up. Interstates became parking lots of stranded vehicles. The power grid started failing. Not because of the snow, but because of the extreme cold combined with peak demand. Transformers failed. Natural gas pipelines couldn't maintain pressure because the gas itself was so cold it wasn't flowing properly. Wind turbines iced over. Even some coal and nuclear plants had to shut down when their water supplies froze. Within 48 hours, over 4 million people had lost electricity. In sub-zero temperatures, in states where homes aren't built for this kind of cold, the death toll climbed. Hypothermia, carbon monoxide poisoning from people burning things indoors, car accidents on ice, elderly people who couldn't get their medications because roads were closed. By the time the storm moved offshore on January 25th, over 600 people were dead. Meteorologists analyzed the storm afterward and concluded it was a natural event. Extreme, yes, Rare, yes, but within the bounds of normal weather variability. The polar vortex disrupts periodically. Cold air escapes. Sometimes it coincides with a developing storm system. Bad luck, essentially. But 600 people died from bad luck that happened exactly 4 days after a massive solar storm hammered Earth's magnetosphere with more energy than we'd seen in years. And exactly 2 days after that solar storm, the atmospheric containment system that keeps Arctic air locked away started breaking. That's the sequence. That's what actually happened. 3 events in 4 days, each one documented and measured. The question is whether physics connects them, or whether we're just seeing patterns in noise. So if the energy didn't just disappear into space, where exactly did those billions of watts go? To understand whether a solar storm can affect weather, you first need to understand that Earth isn't sitting in empty space surrounded by nothing. We're inside an active war zone, and we have been for billions of years. The sun doesn't just shine light at us. It's constantly ejecting material in all directions. Every second, the sun loses about 600 million tons of mass through a stream of charged particles called the solar wind. These are mostly protons and electrons stripped from hydrogen atoms and accelerated away from the sun's surface by heat and magnetic forces. This wind flows past Earth at about 1,000,000 miles per hour during quiet times. During solar storms, it can exceed 2 million, and it's not empty wind. It carries energy, it carries magnetic fields, and it carries momentum. If Earth had no defense, this wind would strip away our atmosphere over millions of years. We know this because it happened to Mars. Mars used to have a thicker atmosphere billions of years ago. Then its magnetic field died when its core cooled. Without protection, solar wind eroded the atmosphere away. Now Mars is a cold, dry desert. Earth's defense is the magnetosphere, generated by electric currents in our liquid outer core. Earth's magnetic field extends far into space, creating a bubble that the solar wind has to flow around. On the sunny side, this bubble extends about 40,000 miles. On the night side, it stretches into a long tail that extends past the moon's orbit. The boundary where solar wind meets magnetosphere is called the magnetopause. It's not a solid wall. It's a dynamic interface where magnetic fields and plasmas interact. Think of it more like the surface of a river flowing around a rock. There's constant turbulence, constant energy transfer, constant adjustment. During normal conditions, this boundary holds steady. The magnetosphere deflects most of the solar wind. Some energy leaks through, but it's manageable. Earth's atmosphere stays intact. Life continues. But during a geomagnetic storm, the dynamics change completely. Here's the critical mechanism. The solar wind carries its own magnetic field, called the interplanetary magnetic field. Usually this field is oriented in various directions as the wind flows past Earth. Sometimes it points north, sometimes south, sometimes east or west. Most of the time it just slides past our magnetosphere without coupling strongly. But when a coronal mass ejection hits, especially one with a strong southward magnetic field, something dramatic happens. On Earth's day side, our magnetic field points north. When the CME's southward field presses against it, the two fields can merge through magnetic reconnection. This is where physics gets violent. Magnetic field lines from the Sun and from Earth connect. Through this connection, energy and particles flow from the solar wind directly into the magnetosphere. The transfer rate can exceed 10 terawatts during major storms. That's more than half of all human civilization's power generation happening as a natural process. The energy doesn't just sit in the magnetosphere. It gets funneled along magnetic field lines toward the poles where those field lines intersect the upper atmosphere. There, it dumps into the ionosphere. January 18th saw one of the most efficient energy transfers in recent years. The CME's magnetic field was strongly southward for over 12 hours. Reconnection was continuous and powerful. Satellite measurements showed the magnetosphere compressed to within 25,000 miles of Earth on the day side, the most severe compression in 3 years. That compression represents enormous energy transfer. When you compress a magnetic field, you do work on it. That work energy has to go somewhere. It went into the ionosphere. The ionosphere is the layer of atmosphere from about 60 to 600 miles up where solar radiation is intense enough to strip electrons from atoms. The air up there is incredibly thin, less than a billionth the density at sea level. But it's electrically conductive because of all those free electrons. When energy from a geomagnetic storm hits the ionosphere, several things happen simultaneously. First, the thin air heats up dramatically. Temperature increases of several hundred degrees are common during major storms. In such thin atmosphere, this causes expansion. The ionosphere puffs up, extending higher into space. This affects satellites by increasing drag. It affects GPS by distorting signals passing through. Second, electric currents begin flowing through the ionized gas. These are called auroral electrojets, and they can carry millions of amperes of current. These currents create their own magnetic fields, which is what ground-based magnetometers detect during geomagnetic storms. Third, the charged particles precipitating into the atmosphere create auroras, but that's just the visible symptom. Most of the energy goes into heating and creating currents, not making pretty lights. During the January 18th storm, instruments measured ionospheric temperatures increasing by over 300 degrees at auroral latitudes. The electric currents flowing through the ionosphere exceeded 2 million amperes. Ground magnetometers in Alaska recorded disturbances over 1,000 nanoteslas, more than 10 times the normal variation. This represents a massive injection of energy into the upper atmosphere, energy that has to cascade downward through the atmospheric layers below. Here's what most weather forecasters don't think about. The atmosphere isn't separate pancakes stacked on top of each other. It's one continuous fluid system. What happens at the top affects the middle, which affects the bottom. The mechanism for this coupling is complex, but it's real. When the ionosphere heats up and expands, it changes the pressure gradient between atmospheric layers. Warmer, less dense air up top means different pressure pushing down on the layers below. More importantly, the energy doesn't just heat the gas locally. It can launch atmospheric gravity waves. These aren't gravitational waves from black holes, different phenomenon entirely. Atmospheric gravity waves are like ripples in water, except the fluid is air and the restoring force is buoyancy instead of surface tension. When you disturb the ionosphere with a massive energy input, you create waves that propagate downward. These waves carry energy and momentum. They travel through the mesosphere, the layer between 30 and 50 miles up. They enter the stratosphere where the polar vortex lives. Laboratory experiments and computer simulations show these waves can have real effects. They can alter wind patterns. They can change temperature distributions. They can deposit momentum in regions far from where they originated. During the January storm, satellites designed to measure atmospheric waves detected strong wave activity, propagating downward from the ionosphere into the mesosphere within 24 hours of the storm's peak. Ground-based radar systems in northern Canada tracked these waves continuing into the stratosphere by January 19th and 20th. Did these waves contribute to the polar vortex disruption that followed? Most meteorologists say the effect is too small. The stratosphere has its own massive energy sources. Waves from the troposphere below typically carry much more energy than anything from above, but that assumes normal conditions. What if the polar vortex was already in a marginally stable state? What if it was close to tipping into disruption anyway, and the waves from above provided just enough extra push? Complex systems can be sensitive to small perturbations when to 10. They're near transition points. The classic example is an avalanche. One snowflake doesn't cause an avalanche, but one snowflake landing on an already unstable snowpack can trigger a catastrophic release. Was the stratosphere on January 20th, like that snowpack, one more input away from transition? But how do we actually measure whether those waves were strong enough to tip the balance? The fundamental physics question here is simple. Where did the energy go? Let's quantify what we're talking about. During the January 18th storm, instruments measured the total energy deposited into the ionosphere at between 10 and 20 gigawatts, sustained over roughly 12 hours. That's between 120 and 240 gigawatt hours of total energy. For comparison, a major hurricane contains about 600 trillion joules of energy over its lifetime. The January solar storm put roughly 500 billion joules into the ionosphere. That's about 1,000th the energy of a hurricane. This is where most meteorologists stop paying attention. They look at that ratio and say the solar storm is negligible compared to the energy already sloshing around in the atmosphere. Weather is driven by the sun heating the surface, which involves thousands of terawatts continuously. Why would a few gigawatts in the ionosphere matter? But that argument assumes energy distributes uniformly and instantly. It doesn't. Energy arrives in specific locations at specific times. It creates gradients, and gradients drive dynamics. When you inject several hundred gigawatt hours into the polar ionosphere over 12 hours, you're not just adding heat. You're creating a localized disturbance that propagates. You're launching waves. You're changing the vertical structure of the atmosphere in ways that can affect circulation patterns. The question isn't whether the total energy is large compared to a hurricane. The question is whether it's large enough in the right place at the right time to nudge a system that's already close to a transition. The polar vortex exists in a state that's often marginally stable during midwinter. It's being constantly pushed and pulled by waves propagating up from the troposphere below. These are called planetary waves, large-scale undulations in the atmospheric flow driven by surface topography and temperature contrasts. When enough planetary wave energy accumulates in the stratosphere, it can disrupt the vortex. The waves break, transferring their momentum to the zonal winds. This slows down the circulation. The vortex weakens, distorts, sometimes splits in two or even collapses entirely. This process is well understood. It happens naturally several times per decade. Most polar vortex disruptions have nothing to do with space weather. They're driven by internal atmospheric dynamics. But here's where it gets interesting. Research over the past 20 years has found statistical correlations between geomagnetic activity and stratospheric changes. Multiple studies using decades of data have shown that major geomagnetic storms are followed more frequently than chance would predict by stratospheric warming events 7 to 10 days later. The correlation isn't perfect. Plenty of geomagnetic storms happen with no stratospheric response. Plenty of stratospheric warmings happen with no preceding space weather. But the statistical signal is there, weak but persistent across multiple independent analyses. A 2016 paper in the Journal of Atmospheric Sciences analyzed 40 years of data and found that when strong geomagnetic storms occurred during winter months, sudden stratospheric warming events followed within 2 weeks, about 30% more often than the baseline rate. That's statistically significant, though the mechanism remained unclear. A 2022 study, using improved atmospheric models, suggested that energy deposited in the ionosphere during storms could launch atmospheric gravity waves with just the right wavelengths to interact with the polar vortex. The waves carry momentum downward. When they break in the stratosphere, they deposit that momentum into the winds, potentially providing the extra push needed to tip an already unstable vortex into disruption. The models showed this was possible, not guaranteed, not even likely most of the time, but possible under specific conditions. If the vortex was already being stressed by planetary waves from below, and if a geomagnetic storm occurred at just the right phase of that stress, the additional forcing from above could trigger earlier disruption than would otherwise occur. January 20th might have been one of those times. When the polar vortex weakens or disrupts, it doesn't immediately affect surface weather. The stratosphere is 10 to 30 miles up. Weather happens in the troposphere below 7 miles, but the two layers communicate. When stratospheric circulation changes, it alters the vertical propagation of waves between the layers. This affects the position and intensity of the jet stream in the troposphere. Over the course of 1 to 3 weeks, changes in the stratosphere propagate downward. The signature is characteristic. You see the jet stream become more wavy, more meridional, as meteorologists say. Instead of flowing smoothly west to east, it develops large north-south excursions. These wave patterns allow Arctic air to plunge far south, while subtropical air pushes far north. This is why polar vortex disruptions in the stratosphere are followed by cold snaps at the surface. Not immediately, but with a lag of 1 to 2 weeks. Except January 2026 was different. The time lag was shorter. The vortex distortion began on January 20th. Arctic air was already flooding south by the 22nd, just 2 days later. Winter storm Fern tapped into that air immediately. The normal week or two delay didn't occur. This suggests the troposphere was already predisposed to the pattern. The storm system that became Fern was already developing. The Arctic air outbreak was already likely given the stratospheric evolution. But the timing may have been accelerated. Did the accelerated timing matter? Absolutely. If the Arctic air had arrived 3 days later, the developing low-pressure system might have moved out before encountering it. The storm might have been moderate instead of historic. Hundreds of people who died might have survived. Timing matters in chaotic systems. Small changes in when things happen can lead to large changes in outcomes. Before we get too excited about this hypothesis, let's be clear about what the mainstream meteorological community thinks. Most atmospheric scientists who study weather and climate are deeply skeptical of any significant connection between space weather and tropospheric weather. They make several strong arguments. First, the energy budget doesn't work in their view. The troposphere receives about 170,000 terawatts of solar energy through normal sunlight. Weather systems like hurricanes and blizzards are driven by this massive energy source. A geomagnetic storm, adding a few gigawatts to the ionosphere, is like pouring a cup of hot water into the ocean and expecting it to affect global ocean circulation. Second, the coupling mechanisms are weak and indirect. Even if atmospheric gravity waves propagate from the ionosphere to the stratosphere, they have to compete with much stronger waves propagating up from the troposphere. The stratosphere is dominated by bottom-up forcing. Top-down effects from space weather are orders of magnitude smaller. Third, polar vortex disruptions happen regularly, without preceding geomagnetic activity. January is prime season for disruptions anyway. The northern hemisphere winter stratosphere is naturally unstable. Finding a disruption that happens to follow a solar storm is like finding it rained after you washed your car. Sometimes it's just coincidence. Fourth, and most importantly, weather forecast models don't include space weather parameters, and they work. They predict storms days in advance with good accuracy using only tropospheric and stratospheric data. If space weather were a significant factor, the models would fail systematically during geomagnetic storms. They don't. The burden of proof, these scientists argue, is on those claiming an effect. Show us the mechanism, they say. Show us the energy pathways that are strong enough to matter. Show us why we should care about a few gigawatts in the ionosphere when there are thousands of terawatts in the troposphere. These are fair points. This is good skepticism. Science should demand strong evidence for claims that challenge established understanding. So where does that leave us? We have statistical correlations suggesting something might be there. We have plausible physical mechanisms showing how it could work. We have one very suspicious case in January 2026, where the timing was almost too perfect. But we don't have proof. We don't have a smoking gun. We can't point to definitive measurements showing that energy from the solar storm directly caused the polar vortex to disrupt, which directly caused winter storm Fern to intensify. What we have is a mystery, a pattern that's either meaningful or noise, a sequence of events that's either physics or coincidence. And here's what makes the mystery more urgent. Even if the effect is small now, even if space weather only matters 1% of the time, or only nudges things slightly when it does matter, that could change, because Earth's magnetic shield is getting weaker. And what happens when the shield that's protected us for billions of years starts failing? Earth's magnetic field has been measured accurately since the early 1800s, when scientists first developed sensitive instruments. Over those 200 years, we've watched the field steadily weaken. The decline isn't dramatic, about 5% per century on average. That means, in your lifetime, the field has weakened by maybe 3 or 4%. You'd never notice directly. The magnetosphere still protects us. Auroras still appear in roughly the same locations. Life continues normally. But extend that trend. In 500 years, at the current rate, the field will be 75% as strong as today. In 1,000 years, 50%. In 2,000 years, 25%. These aren't abstract numbers. A weaker magnetic field means less protection from solar radiation. It means the magnetosphere compresses more easily during storms. It means more energy reaching the ionosphere. It means auroras at lower latitudes, becoming common, not exceptional. The geological record shows this has happened before. Multiple times in Earth's history, the magnetic field has weakened dramatically, even reversed polarity entirely. North magnetic pole becomes south, south becomes north. These reversals happen every few 100,000 years on average. We might be heading into one now, or the field might stabilize and strengthen again. The physics of Earth's core is complex enough that we can't predict with certainty, but the trend right now is clear. Weakening. The weakening isn't uniform across the planet. There's one region where the magnetic field is already dramatically weaker than anywhere else. It's called the South Atlantic Anomaly. Over a vast area stretching from South America across the South Atlantic Ocean toward Africa, the magnetic field strength is about 30% lower than the global average. In some spots, it's 40% weaker. This happens because the magnetic field isn't perfectly aligned with Earth's rotation axis. The magnetic poles don't match the geographic poles. The field is tilted and offset. That geometry creates regions where the field lines are farther from Earth's surface, which means weaker field strength at a given altitude. In the South Atlantic Anomaly, the inner Van Allen radiation belt, a region of space containing energetic charged particles trapped by Earth's magnetic field, dips to within 200 miles of the surface. That's low enough that satellites in low Earth orbit pass through it regularly. Satellites know about the anomaly intimately. When they fly through it, radiation levels spike. Electronics experience more errors. Computers crash more often. Over time, satellites that spend lots of time in the anomaly age faster and fail sooner. The International Space Station passes through the anomaly multiple times per day. Astronauts have reported seeing random flashes of light cosmic rays hitting their retinas even through closed eyelids. The station's sensitive instruments are routinely shut down during anomaly passes to avoid radiation damage. And the anomaly is growing. Satellite measurements over the past 40 years show it expanding westward and weakening further. Some recent data suggests it might be splitting into two separate weak regions. This isn't just a space problem. As the anomaly grows and weakens, more solar radiation penetrates deeper into the atmosphere over that region. During geomagnetic storms, the effects are amplified. What happens if the entire planet's magnetic field weakens to anomaly levels? We'll find out over the next few centuries if the current trend continues. Imagine it's the year 2300. Your descendants are living on an Earth with a magnetic field half as strong as today's. Solar storms that we currently rate as moderate G2 events would hit with the intensity of severe G4 storms. The magnetosphere would compress more easily. More energy would reach the ionosphere during each event. Auroras would appear regularly at mid-latitudes, maybe even in the tropics during major storms. Satellites would be more vulnerable. Power grids would face stronger geomagnetically induced currents. GPS would be disrupted more frequently. Communications would be harder to maintain during space weather events. And if there is any connection between space weather and surface weather, even a weak one, it would become stronger. More energy cascading down means larger effects in the stratosphere. Larger stratospheric effects might mean more frequent or more severe impacts on tropospheric weather. Your descendants might routinely check space weather forecasts alongside Earth weather forecasts. They might prepare for cold snaps or storm intensifications based on solar activity predictions. They might build infrastructure designed to handle not just historical weather patterns, but weather influenced by cosmic forces, or maybe not. Maybe even with a weaker field, the coupling will remain negligible. Maybe weather will stay purely tropospheric. But here's the thing, we're conducting an experiment we can't control. The magnetic field is weakening whether we understand the consequences or not. We're going to find out what happens. There's one planet we know of that lost its magnetic field completely. Mars. 4 billion years ago, Mars had a thick atmosphere and liquid water on its surface. We know this from geological evidence. Ancient river valleys, dried lake beds, minerals that only form in the presence of water. Mars also had a magnetic field. We know this because some of the oldest Martian rocks are magnetized, frozen records of the field that existed when those rocks formed. Then, something happened in Mars's interior. The planet is smaller than Earth, which means it cooled faster. The liquid outer core that generated the magnetic field solidified or slowed its circulation. The dynamo shut down. Without magnetic protection, the solar wind directly impacted Mars's upper atmosphere. Over hundreds of millions of years, the solar wind stripped away most of the atmosphere. The air got thinner and thinner. Eventually, liquid water couldn't exist on the surface anymore. The planet dried out. Today, Mars's atmosphere is less than 1% as dense as Earth's. The surface is bombarded by radiation. It's cold, dry, and essentially dead. Earth won't become Mars. Our planet is larger, our core will stay liquid and active for billions of years more. Even if the magnetic field weakens significantly or temporarily disappears during a reversal, it will come back. But the Mars comparison shows what's at stake. The magnetosphere isn't decorative. It's life support. It's what keeps our atmosphere from slowly bleeding away into space. A weaker field means a more vulnerable atmosphere. Not on human timescales, but it matters for the long-term habitability of our planet. We're living through a transition period. The magnetic field is changing, weakening, possibly preparing to reverse. This process takes thousands of years, far longer than human civilization has existed. But we're the first humans with instruments good enough to measure it happening. We're the first to understand what it means. And we're the first who might be able to prepare for the consequences. Right now, the shield still works. We're still protected. But every solar storm that hits is hitting a slightly weaker defense than the previous storm. Every geomagnetic event penetrates slightly deeper. Every burst of solar radiation deposits slightly more energy into our atmosphere. If space weather affects Earth weather even marginally, now that effect will grow. Slowly but inexorably, as the shield continues to fade. So in a universe where nothing sits still, where do we actually stand? Step back. Way back. Let's see where we actually are. Earth orbits 93 million miles from the Sunday. That sounds like we're separate objects, the Sun over there and Earth over here with empty space between. But that's not accurate. The Sun has an atmosphere that extends billions of miles into space. It's called the heliosphere, and it reaches past Pluto. Every planet in the solar system orbits inside the Sun's atmosphere. The solar wind isn't happening somewhere else. It's happening here. Right now, as you listen to this, solar wind plasma is flowing past Earth at 1 million miles per hour. Not past us in some distant sense. Flowing through the space around our planet, pressing against our magnetosphere, trying to get through. We're inside an active star's outer atmosphere. We've always been. The distinction between space and Earth is a human construction. Physically, there's just a gradient. More particles here, fewer there. Stronger magnetic field close to Earth, weaker far away. The magnetosphere isn't a wall separating us from space. It's a region where Earth's magnetic field is strong enough to partially deflect the solar wind, creating a calmer zone for the atmosphere to exist within. But deflection isn't isolation. Energy crosses the magnetopores constantly. Particles leak through. The two systems interact every second. January 18, 2026 was just one moment when that interaction became violent enough for us to notice. But the interaction never stops. The coronal mass ejection that hit Earth that day carried the kinetic energy of billions of nuclear weapons. 1 billion tons of plasma traveling at 2 million miles per hour. When it collided with the magnetosphere, the impact was spectacular in terms of physics. Magnetic fields compressed. Energy transferred at terawatt levels. The magnetopores moved 25,000 miles closer to Earth in hours. That's half the distance to geosynchronous satellites compressed away. And it's not a rare event. Major geomagnetic storms happen every few years. During solar maximum, they can happen multiple times per year. The Sun regularly throws this kind of violence at us. Most of the time we don't notice directly because the magnetosphere absorbs the impact. The system is designed for this. 4 billion years of evolution under these conditions means life is adapted to them. But adapted to doesn't mean unaffected by. Adaptation means survival, not immunity. Energy from a solar explosion races across space as plasma. It hits the magnetosphere and transfers terawatts of power through magnetic reconnection. That power dumps into the ionosphere as heat currents and particle precipitation. The ionosphere responds by heating, expanding, launching atmospheric gravity waves downward. Those waves propagate through the mesosphere, carrying energy and momentum. Some of that reaches the stratosphere, where it might interact with circulation patterns like the polar vortex. If the stratosphere is disturbed, effects propagate to the troposphere over days to weeks. Jet stream patterns change. Weather systems that were going to form anyway might form differently at different times with different intensities. Each step in this chain is observed. Energy transfer to the magnetosphere measured. Energy deposition in ionosphere measured. Atmospheric wave generation observed. Wave propagation to stratosphere tracked. What's not proven is whether the final steps matter quantitatively. Whether the energy and momentum reaching the stratosphere is enough to significantly alter weather outcomes. Whether the timing and location are ever right for it to make a difference. But the pathway exists. The physics allows it. Energy flows from sun to magnetosphere to ionosphere to mesosphere to stratosphere to troposphere. From explosion 93 million miles away to snowflake falling on your roof, one continuous chain of physical processes. On January 15th, a sunspot erupted. The sun does this constantly, but this eruption happened to be aimed at Earth and happened to be large. 3 days later, the plasma arrived. Earth's magnetic field happened to be oriented for efficient reconnection. The storm was severe, but not unprecedented. 2 days after that, the polar vortex, which had been stable for weeks, started distorting. Maybe this was already going to happen due to planetary waves building up from below. Maybe the waves from the geomagnetic storm provided an extra push. We can't tell from one event. 2 days later, a storm system forming over Oklahoma tapped into the Arctic air released by the vortex disruption. The temperature contrast was extreme. The storm explosively deepened into Winter Storm Fern. 600 people died over the next few days. Mostly elderly, mostly poor, mostly in homes that weren't built for that kind of cold in regions that don't normally see it. Would those 600 people still be alive if the solar storm hadn't happened? We have no way to know. Probably the blizzard would have formed anyway, maybe slightly weaker, maybe a day later. But maybe not. Maybe the coincidence was real. Maybe space and Earth weather connected in ways we don't yet understand, and the result was measurably worse because of it. The system is too complex to know from one case. The universe doesn't respect our categories. We divide things into space physics and atmospheric physics because it makes the science manageable. We study the ionosphere separately from the troposphere because they operate on different scales and time constants. But nature doesn't care about our organizational charts. Energy flows where physics allows it to flow. Waves propagate through whatever medium will carry them. Systems couple when the conditions permit coupling. The sun affects Earth. Obviously, it does through radiation. We know heat drives weather, but could it also affect us through magnetic storms, through energy deposited in the upper atmosphere that cascades down? The answer appears to be maybe, sometimes under specific conditions, weakly indirectly, but perhaps not negligibly. This isn't the universe we were taught about. We were taught that space and weather are separate, that cosmic forces affect us through gravity and light, nothing else, that everything important for daily life happens within Earth's atmospheric bubble. But the data keeps suggesting the universe is more interconnected than that, more subtle, more complex. A storm on the sun ripples outward as plasma. 93 million miles later, it hits Earth's magnetic field. Energy cascades down through atmospheric layers. Days later, it might snow in Dallas. One system, sun to snow, space to surface, the vast to the mundane. But what does this cosmic connection actually mean for people just trying to live their lives? Modern civilization is extraordinarily efficient and extraordinarily fragile. Two sides of the same coin. We've optimized every system to run just in time, just enough capacity, just within normal bounds. This makes everything cheaper, faster, more profitable. But it also means there's no slack, no redundancy, no margin for conditions outside the design envelope. The power grid is designed for peak historical demand, plus maybe 10% margin. When demand exceeds that during extreme cold, something has to give. Transformers overload. Circuits trip. Rolling blackouts begin, then cascading failures. Natural gas pipelines are sized for typical winter flow. When temperatures drop beyond the historical range, pressure drops too. The gas is so cold it doesn't flow properly. Delivery falls short right when demand is highest. Water treatment plants assume pipes won't freeze. Why would they, in regions where temperatures historically stay above freezing most winters? So they're not built with the heating and insulation needed for extreme cold. When polar air reaches places, it normally doesn't go, pipes burst, treatment stops, boil water orders go out. Transportation assumes roads will be passable with normal snow-clearing resources. Cities in the south don't own many snowplows because they don't usually need them. When 18 inches falls in Dallas, the city simply stops functioning. Supply chains assume trucks can keep moving. Warehouses hold maybe 3 days of inventory because just-in-time delivery means you don't waste money storing things. When roads close for a week, shelves empty fast. Winter Storm Fern didn't break these systems through unprecedented force. It broke them by pushing conditions just past the bounds they were designed for in regions that aren't equipped for those conditions. Dallas hit 8 degrees Fahrenheit. That's cold, but not unheard of. Places in Minnesota see that regularly and handle it fine. The difference is Minnesota builds for it. Dallas doesn't. Storm forecasts gave people 3 days warning, enough time to stock up on supplies, charge batteries, prepare. But if the storm had been 2 days later, some of those people would have had different timing, been in different places, made different decisions. Chaos theory tells us small changes in initial conditions lead to large changes in outcomes. The butterfly effect isn't just metaphor, it's how nonlinear systems actually work. Maybe if Winter Storm Fern had formed on January 24th, instead of 22nd, 50 people who died would have survived. Maybe a power plant that failed would have stayed online 2 more days keeping heat on for a neighborhood. Maybe a stranded driver would have made it home before the roads became impassable. We can't know, we can never know, but the possibility should bother us. If space weather can nudge Earth weather timing even slightly, those nudges matter in a civilization with no margin for error. Our infrastructure planning uses historical data. Engineers look at the worst conditions observed in the past century, add some margin, and design for that. This works reasonably well for gradually changing conditions. As climate shifts, as statistical patterns evolve, we periodically update the standards and rebuild things stronger. But it doesn't work for influences we don't know about. If space weather affects Earth weather, and we're not accounting for it, we're systematically underestimating risk in our designs. Power grids designed assuming geomagnetically induced currents only affect high-latitude regions might be vulnerable at mid-latitudes during major storms if the magnetic field continues weakening. Emergency response systems designed assuming weather follows only tropospheric patterns might not have enough warning time if space weather adds another driver that changes onset timing. Agricultural planning designed around historical climate patterns might miss changes if solar activity influences circulation in ways we don't yet model. Insurance and financial systems designed around historical disaster frequencies might misprice risk if space weather-influenced events become more common as the shield weakens. These aren't imaginary concerns. After the January storm, reinsurance companies started asking questions. If this is the new normal, if 600-death winter storms can happen when conditions align right, their risk models need updating. But you can't update models when you don't understand the mechanism. If space weather matters, we need to know how much and under what conditions. The scientific community is working on this slowly. Research groups are combining atmospheric and space weather data. New instrument networks are being deployed to monitor the entire atmospheric column during geomagnetic storms. Computer models are being developed that span from magnetosphere to surface. But research takes time and money. Solar storms don't happen on convenient schedules. You have to wait for nature to provide the events, then analyze what happened. Building statistical certainty requires decades of data. Meanwhile, we keep building infrastructure on assumptions that might be incomplete. Billions of dollars of investment based on models that might be missing a piece. If the connection between space and Earth weather is real and significant, we'll find out eventually. Maybe in 5 years when enough data accumulates. Maybe in 50 years when the magnetic field is noticeably weaker and effects become obvious. The question is whether we find out through careful research or through repeated disasters. 600 people died. Real humans, with families and lives, and futures that ended because they got too cold. Most of them were elderly. Many were poor, living in homes with insufficient heat in regions where nobody expected that kind of cold. The deaths were preventable with better infrastructure, better preparation, better warning. We pride ourselves on being advanced. We have weather satellites, forecast models, early warning systems. We think we understand how weather works well enough to predict it days in advance and build for it. But if a solar storm 93 million miles away contributed to those 600 deaths, even indirectly, even slightly, then we don't understand the system as well as we think we do. And the next solar maximum is coming. More storms. More chances for cosmic and terrestrial forces to align. More opportunities for our incomplete understanding to fail us. So as we watch the sun gear up for its next active phase, what should we actually be paying attention to? Science progresses through argument. When scientists disagree, when they demand better evidence from each other, when they defend different hypotheses vigorously, that's not science failing. That's science working exactly as it should. So, when you ask whether space weather can influence Earth weather, you're asking a question that currently divides two scientific communities that rarely talk to each other. Meteorologists spend their careers studying the troposphere and stratosphere. They understand cyclones, fronts, jet streams, moisture transport. They build models that predict weather days in advance with impressive accuracy. And they'll tell you that space weather is irrelevant to their work. The argument is straightforward. Weather is driven by massive, obvious energy sources. The sun heats the Earth's surface unevenly. Tropical regions receive more energy than polar regions, creating temperature gradients. Those gradients drive wind. Wind transports moisture from oceans to continents. Moisture condenses into clouds and precipitation. The Earth's rotation adds the Coriolis effect, creating cyclones and anticyclones. All of this involves enormous amounts of energy and very well understood physics. You can model it, you can predict it, you can watch it happen in real time with satellites and radar. Now add a geomagnetic storm. It puts a few gigawatts into the ionosphere, 60 miles up at high latitudes. The ionosphere is above 99% of the atmosphere's mass. It's essentially in space, as far as weather is concerned. How is that supposed to affect a storm system in the troposphere, driven by hundreds of terawatts of surface heating? The meteorologists have run the numbers. Even if you assume perfect coupling, which doesn't exist, the energy from space weather is negligible. It's like trying to change the temperature of a swimming pool by heating a thimbleful of water and pouring it in. The scale difference is too large. Moreover, forecast models work without including space weather. The European Centre for Medium-Range Weather Forecasts runs the most sophisticated weather model in the world. It ingests millions of observations daily, from satellites, weather stations, aircraft ships. It simulates atmospheric physics on a grid, with spacing down to 9 kilometers. It can predict weather patterns a week in advance with skill. The model doesn't know about geomagnetic storms. It doesn't include ionospheric parameters. It doesn't care what the sun is doing beyond normal solar radiation. And it works. If space weather mattered for tropospheric weather, the model should fail more often during geomagnetic storms. Forecasts should become less accurate. The predictions should miss important developments. They don't. Statistical analysis shows no correlation between forecast skill and space weather activity. The conclusion seems clear. Space weather affects the ionosphere and magnetosphere. It can damage satellites, disrupt communications, create beautiful auroras. But it doesn't affect weather where people live. Winter Storm Fern was a natural event. Strong, but within historical variability. The fact that it happened after a solar storm is coincidence, nothing more. Talk to scientists who study the ionosphere and magnetosphere, and you hear a different perspective. They don't claim space weather causes surface weather. They're too careful for that. But they see pathways for influence that meteorologists might be dismissing too quickly. The argument starts with energy conservation. When a geomagnetic storm deposits 10 gigawatts into the ionosphere for 12 hours, that's real energy being added to the Earth system. It heats gases, creates currents, launches waves. Physics says that energy propagates, it doesn't just sit there. Atmospheric gravity waves are observed phenomena. We've measured them with satellites and radar. We've watched them propagate from the ionosphere, down through the mesosphere, into the stratosphere. They carry energy and momentum. When they break, they deposit that momentum into the background wind field. Could that momentum deposition matter? Maybe not under normal circumstances. But what about when the stratosphere is already in a marginally stable state? The polar vortex isn't a solid object. It's a circulation pattern maintained by temperature gradients and planetary wave forcing. It exists in a state that can be tipped into disruption if enough momentum is added in the right way at the right time. Think of it like a spinning top. When it's spinning fast and stable, small perturbations don't matter. But when it's already wobbling, when it's close to falling over, even a small push can tip it. Several research groups have found statistical evidence that geomagnetic storms correlate with subsequent stratospheric changes. Not every time, not even most of the time, but more often than random chance would predict. That correlation demands explanation. The space physics community also points out that the coupling between atmospheric layers is poorly understood. Most weather models don't extend above the stratosphere. They don't simulate the mesosphere or ionosphere at all. How can meteorologists be confident there's no coupling when their models don't include the upper layers? Recent research has shown that the stratosphere is more sensitive to top-down forcing than previously thought. Studies using models that do extend to the ionosphere have found that under certain conditions, energy input from above can influence stratospheric circulation. It's not simple. It's not direct, but it's possible. The space physicists aren't claiming they understand the full mechanism yet. They're saying the question deserves more research, not dismissal. They're saying that absence of evidence isn't evidence of absence, especially when we haven't looked carefully. Part of the problem is institutional. Meteorology and space physics are different disciplines. They're taught in different departments. Researchers attend different conferences. They publish in different journals. Meteorologists are experts in the troposphere and stratosphere, but rarely think about the ionosphere. Space physicists are experts in the ionosphere and magnetosphere, but rarely think about weather. The region where coupling might occur, the mesosphere and upper stratosphere between 30 and 60 miles altitude, falls between these two communities. It's not studied intensively by either group. So when someone asks, can space weather affect Earth weather, the question literally falls into a gap. The meteorologists say it's not their domain and seems unlikely. The space physicists say it's not their domain but seems possible. Nobody owns the question. There have been attempts at collaboration. Some research groups now include both meteorologists and space physicists. Some new models are being developed that simulate the entire atmosphere from the ground to 300 miles up, but it's slow work. Science funding is competitive, resources are limited, and most funding agencies prioritize research with clear applications. Weather forecasting has obvious applications. Space weather forecasting for satellites has obvious applications. The question of whether they interact is more esoteric, unless, of course, that interaction is real and significant. Then it becomes extremely applied. Then it affects millions of people's lives. Both sides agree we need better data. Specifically, we need simultaneous measurements of the entire atmosphere during major geomagnetic storms. Instruments tracking the ionosphere, the mesosphere, the stratosphere, and the troposphere all at once with high time resolution. We need to watch energy cascade down, measure the waves being launched from the ionosphere, track them as they propagate through the mesosphere, observe their interaction with stratospheric circulation, see if and how they affect the polar vortex. We need more events. January 2026 is one case. That's not enough. Science needs multiple examples to establish causation. We need to observe several more instances where a strong geomagnetic storm precedes unusual stratospheric or tropospheric behavior. We also need better models that can simulate the physics from the magnetosphere down to the surface with high resolution. Models that include all the coupling mechanisms, electromagnetic effects, atmospheric waves, chemical changes. These models exist in pieces. There are excellent magnetosphere models. There are excellent ionosphere models. There are excellent weather models, but they're rarely connected. Building coupled models that span all these domains is technically challenging and computationally expensive. Finally, we need time. This kind of research takes years. You have to wait for solar storms to occur naturally. You can't create a geomagnetic storm in a laboratory to test your hypothesis. Nature has to cooperate. The good news is that we're approaching solar maximum, the peak of the sun's 11-year activity cycle. Over the next few years, we'll have more major geomagnetic storms, more opportunities to observe what happens afterward, more data to test the hypothesis. So, here's the honest truth. We don't know if the January 18th solar storm contributed to Winter Storm Fern. The timing is suspicious. The mechanisms are plausible, but plausibility isn't proof. Maybe in 5 years we'll have enough data to say yes, there's a connection, or no, it's coincidence. Maybe in 10 years, weather models will routinely include space weather parameters because we've proven they matter. Or maybe research will conclude the effect is too small to worry about. Right now, today, the question is open, the mystery unsolved. And while scientists debate what's actually changing above our heads right now, we're living through a transition period that most people will never notice, but that future generations will look back on as significant. The magnetic field is changing. The sun is cycling through its activity phases. And we're the first humans with instruments good enough to watch it all happen in real time. Science hasn't answered whether the January 18th solar storm caused or contributed to Winter Storm Fern. The data is suggestive but not conclusive. The mechanisms are plausible but not proven. The timing is suspicious but could be coincidence. This might frustrate you. We started with a mystery and we're ending with uncertainty. No clean resolution, no definitive answer. But this is how science actually works most of the time. Not with eureka moments and sudden certainty, but with gradual accumulation of evidence, competing hypotheses, arguments over interpretation. The question of whether space weather affects Earth weather is an active area of research. Multiple groups are investigating it from different angles. Data continues to accumulate. Models improve. Our understanding deepens slowly. Maybe in a decade we'll have a clear answer. Maybe the question will remain ambiguous for much longer. Complex systems often resist simple explanations. What we do know is that the possibility is real enough to warrant investigation. The consequences are significant enough to matter, and the trend toward a weaker magnetic field makes the question increasingly urgent. There's something profound about recognizing how much we don't know. Modern life creates an illusion of understanding and control. We predict weather, navigate by GPS, communicate instantly across the planet. Technology makes it seem like we've figured everything out. But we haven't. We're still discovering basic things about how our planet works. Still finding connections we didn't know existed. Still surprised by the complexity of systems we thought we understood. The atmosphere is one of those systems. We can forecast weather reasonably well a few days out, but our understanding is far from complete. We're still learning how different layers couple, still discovering mechanisms that might matter, still finding that reality is more interconnected than our models assumed. This should be humbling, not frightening. The universe is under no obligation to be simple enough for us to understand quickly. If it takes us centuries to figure out whether space weather affects Earth weather significantly, that's just how long it takes. We're not on some deadline where we have to understand everything immediately. We're at the beginning of a long investigation that future generations will continue. Whether or not space weather triggers Earth weather in a strong causal sense, we've learned something important through this investigation. We've learned that we live in a more connected system than we usually think about. Energy from the sun reaches us through radiation, obviously, but it also reaches us through plasma streams, through magnetic storms, through complex interactions between the solar wind and Earth's magnetic field. Those interactions deposit energy into the upper atmosphere constantly. Most of the time, that energy dissipates in the ionosphere and goes no further. But sometimes, under certain conditions, it might cascade down. It might launch waves that propagate through atmospheric layers. It might nudge systems that are already close to transition points. Even if the effect is small, even if it only matters 1% of the time, or only changes outcomes slightly, it's real. It's part of how the system operates, and we need to include it in our models if we want to understand the full picture. The broader lesson is that boundaries are often artificial. We separate space physics from atmospheric physics for practical reasons because they're too complex to study together. But nature doesn't respect that separation. The magnetosphere isn't a wall. The ionosphere isn't a ceiling. They're regions where different physical processes dominate, but they're all part of one continuous system. Earth isn't an island floating in empty space. We're embedded in the sun's atmosphere. We're constantly interacting with cosmic forces. We're part of the solar system in a much more immediate sense than most people realize. Throughout this investigation, we've encountered enormous scales, billions of tons of plasma, millions of miles per hour, terawatts of power, distances that dwarf human experience. It's easy to feel insignificant against those scales. You're a single human weighing maybe 150 pounds, living for maybe 80 years on a planet that's a tiny dot in a vast cosmos. But insignificance and unimportance aren't the same thing. You are small, yes, but you're also a configuration of matter, complex enough to understand what's happening. You can listen to this investigation and grasp that a solar storm might influence weather. You can comprehend distances of 93 million miles and energy transfers of gigawatts. That understanding itself is remarkable. The universe has arranged matter in such a way that part of it, the part that's you can observe and comprehend the rest of it. That's not insignificant. That's extraordinary. And your life is lived at the human scale where these cosmic forces have real consequences. 600 people died in a blizzard that might have been influenced by a solar storm. Those were real deaths, real suffering, real human tragedy. The cosmic scale matters because it affects the human scale. That's why we investigate these connections. Not out of abstract curiosity, though, that's valuable too, but because understanding the system better might help us protect people better. The sun will have another major eruption. Maybe next week, maybe next year, certainly within the next solar cycle. Another coronal mass ejection will race toward Earth. Another geomagnetic storm will compress the magnetosphere and dump energy into the ionosphere. When that happens, scientists will be watching. Instruments will record the energy deposition. Models will track atmospheric responses. Researchers will look for correlations with subsequent weather patterns. Slowly, over repeated events, statistical patterns will emerge or fail to emerge. The hypothesis will be supported or refuted through accumulated evidence. And you'll be able to watch this process happen. When news reports mention a major solar storm, you'll wonder what might happen to weather in the following days. You'll pay attention to whether vortex disruptions follow. You'll notice if unusual weather systems develop with suspicious timing. You'll be participating in the investigation in a small way. One more observer aware of the questions, watching to see how nature answers them. Years from now, when you think back on Winter Storm Fern, you might remember it differently than others who experienced it. Most people will remember the cold, the power outages, the disruption. It will be categorized as a natural disaster, an extreme weather event, bad luck. But you'll remember the solar storm 4 days earlier, the Auroras in Texas, the polar vortex breaking at suspicious timing, the unanswered question of whether these events connected. You'll remember that science didn't have a definitive answer, that researchers were divided, that the possibility was real enough to take seriously but not proven enough to be certain. And you'll carry that uncertainty forward. Not as something frustrating, but as something true. The world is more complex than our current understanding. Questions remain open. Mysteries persist. That's not a bug in reality. That's the nature of existence in a universe rich enough to keep surprising us. So what does it actually mean to live on a planet whose shield is slowly fading? We've reached the end of this investigation, but the story continues. The sun doesn't care about our debates. It's going to keep doing what stars do, Solar cycle 26 is approaching its maximum over the next few years. The sun's activity is increasing. Sunspots are becoming more frequent. The probability of major coronal mass ejections is rising month by month. We're going to have more geomagnetic storms. Multiple G4 events are likely. Maybe even a G5, which we haven't seen in decades. Each one will be an opportunity to test the hypothesis. Researchers are ready. New instruments have been deployed specifically to monitor the entire atmospheric column during space weather events. Satellite networks are in place. Ground-based radar and magnetometers are collecting data continuously. When the next major solar storm hits, we'll have better observations than we had for January 26, better measurements of ionospheric heating, better tracking of atmospheric waves, better monitoring of stratospheric response. The data will accumulate, patterns will emerge or they won't. If 5 years from now, we've observed 10 major geomagnetic storms and 3 of them were followed by stratospheric disruptions within days, that starts to look like a real pattern. If none of them show that connection, the hypothesis weakens. Science will progress the way it always does, slowly, methodically, through repeated observation. The question won't be answered in a single dramatic discovery. It'll be answered through the patient accumulation of evidence over many events. Meanwhile, the magnetic field continues its slow decline. Every year roughly 0.05% weaker than the year before. Imperceptible in the short term, significant over centuries. Your children probably won't notice any difference in their lifetimes, but your great-great-grandchildren might grow up in a world where auroras regularly appear at latitudes we consider impossible today, where space weather warnings are as routine as weather warnings, where the boundary between cosmic and terrestrial feels more permeable than it does now. They'll look back at this era and recognize it as the beginning of the transition. The time when humans first had the tools to measure what was happening, but before the effects became obvious enough that everyone understood. They'll study the data we're collecting now. They'll use it to understand how Earth's magnetosphere behaves during a weakening phase. They'll build their infrastructure with that knowledge, designing for a future where the shield is thinner and solar storms penetrate deeper. Or maybe the magnetic field will stabilize. Maybe the weakening will reverse. The geological record shows that magnetic field strength fluctuates. Sometimes it drops, sometimes it recovers. We can't predict with certainty what our field will do over the next 1,000 years. All we can do is keep measuring, keep watching, keep trying to understand the dynamics. But here's what we do know for certain: whether or not the January solar storm influenced the blizzard, whether or not space weather regularly affects Earth weather, we've learned something valuable through this investigation. We've learned that the system is more complex than we thought. That the neat categories we use, space versus atmosphere, cosmic versus terrestrial, are human constructions that don't fully capture physical reality. We've learned that energy connects things across scales we usually don't consider. That a magnetic explosion on the sun can deposit power into our ionosphere. That waves can propagate from ionosphere to stratosphere. That stratospheric changes can affect tropospheric weather. Even if each link in that chain is weak, even if the total effect is small, the pathway exists. The connections are real, and we've learned to be humble about what we understand. The meteorologists are right that weather models work well without including space weather. But the space physicists are right that energy has to go somewhere, and coupling mechanisms exist. Both perspectives are valid. Both teach us something. The truth is probably somewhere in the middle, more nuanced than either extreme. Maybe space weather influences Earth weather weakly, occasionally under specific conditions that don't happen often. Maybe it matters 5% of the time, or 1% or less. But if it matters at all, if it contributed even slightly to Winter Storm Fern, then 600 deaths might be partly attributable to cosmic forces we're only beginning to measure. That's worth understanding better. That's worth continued research. That's worth building better models and deploying better instruments and waiting patiently for nature to provide more test cases. The universe keeps teaching us that everything connects, that the boundaries we draw are provisional, subject to revision as we learn more. That complexity hides in places we haven't looked carefully. January 26 gave us one very clear example to investigate. One case where the timing was too perfect to ignore. One sequence of events that demands explanation. Maybe it was causation. Maybe it was coincidence. But either way, it's pushed science forward. It's made us look more carefully at connections we were ignoring. It's opened up new lines of research that will continue for decades. The next time a major solar storm hits, you'll know to pay attention not just to satellite warnings and aurora forecasts. You'll watch for what happens in the days that follow. Will the stratosphere respond? Will weather patterns shift in unusual ways? Will we get another winter storm, Fern? Another suspicious coincidence that adds to the pattern? Or will it become clear that January was just bad luck, 3 unrelated events that happened to align? Time will tell. Nature will provide the answer. And humans will keep watching, keep measuring, keep trying to understand. Because that's what we do. We ask questions about how things work. We gather evidence. We build models. We test hypotheses. We argue about interpretation. And slowly, gradually, over generations, our understanding deepens. You're living through a moment in that long process. The moment when we first asked seriously whether space weather and Earth weather connect. The moment when we had the tools to investigate, but before we had the answer. Future scientists will look back at the data being collected now and see it as the foundation for whatever we eventually discover. And maybe, decades from now, when the magnetic field is noticeably weaker and solar storms routinely penetrate deeper, when the patterns have become clearer and the connections better understood, people will remember January 2026 as the case that started it all. The winter, when a solar storm hit on the 18th, a vortex broke on the 20th, and a blizzard killed 600 people on the 22nd. The winter, when we first seriously asked whether the sun and the snow might be connected by more than just light and heat. Whether cosmic forces 93 million miles away might reach down through invisible pathways and touch the weather we experience on the ground. The answer is still forming. The investigation continues. The sun keeps storming. The shield keeps weakening. And we keep watching, wondering, trying to understand our place in a universe that's vastly more interconnected than we ever imagined.